Hi and welcome everyone to the fourth or fifth, depending on how you count, part of the ultra high vacuum technology for atom probe lecture. In this part, what we're going to be looking at is vacuum measurement. So, vacuum measurement means we're going to have some rough vacuum measurement, um, which is essentially based on measurement of some kind of pressure, some kind of gas property as a whole. And that can be either the gas pressure as in the physical pressure. It can be via some thermal conductivity, some convection cooling, which is the Pirani gauges, or also via piezo gauges, which is again just the pressure. Which I think I will leave out in this lecture just simply because they haven't been used in atom probe, but we might see them at some point in the future. Just simply because they're really handy. And then we'll go and look into high vacuum measurement, and the high vacuum measurement is based on ionization, essentially always. So you can either have hot filament ionization, so you have a hot filament and produce the ions that way, or you have a cold cathode, which is field ionization. So essentially like a field ion microscope. And of course we have combination gauges, which are a combination usually of a Pirani gauge and a hot or a cold cathode gauge. And the first thing I want to say about pressure vacuum measurement is, so one thing I'm also leaving out here is actual partial pressure measurement, residual gas analyzers and the like, because that would just drag the lecture on even more. So if you want to know what your residual gas actually is, you can do that as well, and that becomes more and more popular as well. We are just going to be talking about pressure measurement. And what I want to say about that is, don't believe everything you read. So if your vacuum level shows you a certain number, you really have to think about what that number means, especially when we go down to very low pressures, where we essentially, unless you have a residual gas analyzer, we do not have direct means to know what the partial pressures are. And the gauge will react differently to different partial pressures from different gases, but we'll go through that. And that's something that is actually really important for us in atom probe tomography, because our experiment will react differently to different contaminations. So yeah, don't believe everything you read. So if we look at the different measurement methods that we have available in this case, we can again draw a little graph, or let's call it gauges. Or gauge types. And with the gauge types, we can go and say, okay, at the lower end, at the higher end, we're at ambient pressure. Yeah, so 10 to the 3 millibars. Then we would have 10 to the 0 millibars. Then we would have 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. And I've wrote millibar everywhere. So this is pressure millibar. And then we'll have 10 to the minus 12. And essentially, so if we start at the higher end of pressures, so up to about a millibar, we can use direct mechanical. So that would be our Bourdais manometer, our Bourdais gauge. I hope I'm saying that right. The French people probably say that's not quite true. Then down to about 10 to the minus 4 to 10 to the minus 5 from from ambient pressure on. We'd have our Pirani's, our Pirani gauges. And this is sort of slowly expanding towards lower pressures. Really, really nice would be a Pirani that goes down to 10 to the minus 6. then capacitive gauges can get us down to about 10 to the minus 5 to 10 to the minus 6. Capacitive, and these are piezo capacitives. We're not going to go into the details, but always only section wise. Yeah? So if I buy a piezo gauge that goes down to the 10 to the minus 6, it might just only go from 10 to the minus 6 to 10 to the minus 3 or something like that. Yeah. So they only give us sections of the entire spectrum here. Then we have up to about 10 to the minus 10-ish, 10 to the minus 11. We have, and starting at about 10 to the minus 5. Starting around about here. From here, we have cold cathode gauges. And down to about 10 to the minus 12, we have hot cathode gauges. We have hot filament, hot cathode. And what you can already see is that there is not really any pressure gauge that can get us all the way from ambient pressure down to ultra high vacuum. We can have combination gauges, so-called wide range gauges. Yeah. Wide range gauge. And the wide range gauges can get us from ambient pressure to roughly about 10 to the minus 9. And they're usually a combination of hot filament and cold hot filament gauges and Pirani gauge, or cold cathode gauge and Pirani gauge. The reason why this is important to know is that if you have a wide range gauge, which you will usually have on a load lock, then at some point the pressure measurement will look like it's screwed up. So it will go, it will read some pressure and then just jump to some other pressure. And the reason for that is that it goes from the range where the Pirani is active to the range where the cold cathode gauge or the hot filament gauge is active. Usually in load locks we have combinations of Pirani gauges and cold cathode gauges. Good. Let's jump right into and start at the measurement for the coarse vacuum measurement. Let's start with the Bourdon gauges and the Pirani gauges. And they are actually relatively simple gauges. So the Bourdon gauge is Bourdon gauge is essentially literally just a tube that's sort of round in a semicircular fashion, and then you have attached it to something with, with a hole drilled in it. So, that the pressure P can come in, and with the pressure P, what you get is that the whole thing just then springs open a little bit, and you can use that to attach some kind of mechanical device, so that if if that pulls up, your needle moves. Usually there's a little bit of a gear. So there's some gears in there, so that you use the entire range of motion that a needle can have. 300 degrees or whatever. But this is essentially the way it works, and this means they are cheap, robust, and they're gas agnostic. So it doesn't matter because it's mechanical. It doesn't matter whether you put which gas you put in. You just measure its pressure, and this really makes them very helpful for any coarse vacuum measurement. But the mechanical principle, if you just go force is pressure divided by area, and we are logarithmically going through that. So most of the force is gone once you're at a millibar. At a millibar, that's already 1/1000th of the pressure of ambient conditions. So measuring the force becomes pretty difficult. But yeah, you can make them pretty easily, pretty robust, and also bakeable and God knows what. Yeah. And one of them costs about, if you buy a cheap one that's made for general purpose vacuum measurement in engineering, it costs about $12. If you buy a really expensive one for ultra vacuum sciencey things, it might cost you $200, 200 euros or something like that. It's not super expensive. The next thing for measurement are the Pirani gauges. And Pirani gauges use an electrical measurement principle. So essentially what a Pirani gauge is just a wire. Yeah? And in the wire, you use a current, an electrical current I that you run through, and you will get some heat loss. So essentially just convection of whatever gas you have in there that then cools the wire. And from measuring the resistivity of the wire, so essentially measuring the amount of voltage you need to drive the current or some similar principle, you can actually sorry, I drew over the logo again. I'll just move that out of the way. That is a bit annoying if I do that. I am very sorry about that. So Pirani gauges are just have some loss in there, but you can already see that obviously this is no longer gas independent, because different gases have different convective properties. They have different heat capacitances. And so if we go pressure versus pressure reading, pressure versus pressure reading, then you will see at low temperatures, at low pressures, there's not that much difference, but at high pressures we'll get some deviation depending on whether it's a relatively light gas like helium, something that's sort of what a gauge is calibrated against, which is going to be air, nitrogen, and air, or if it's something heavier like something heavier like argon, right? And this will start roughly, between 10 between 1 and 10 millibar. These deviations will start at low pressures. That the readings are pretty okay. And for Pirani gauges, we have different limits, lower limits. So regular Pirani, and we call them pigs. A regular pig will go. Oh, sorry again. A regular pig will go down to around 10 to the minus 3 millibar. Then they're so-called pulse pigs. So essentially they run pulse, they ramp the current up in a sawtooth fashion. Why that helps, I'm not entirely sure. I haven't looked into detail, but they will get you down to about 10 to the minus 4 millibars. And you can get MEMS Piranis now down to around 10 to the minus 5 millibar. Now, so we're only about an order of magnitude away from what we really want to have, because 10 to the minus 6 is roughly where an SEM works or where a lot of coating systems work. And it would be really nice if in these systems we could get away with having only a Pirani gauge. And what I will show you now, actually in my usual show and tell, is what such a Pirani gauge looks like. And in this case, it's a MEMS Pirani. So you can see here, this is the gauge, and it's very nice, very small, and very compact. And this is really the nice thing about the Piranis, that they are small and compact, and they can, and they can give you really good pressure measurements in that really small form factor. It doesn't need a lot of power either. It needs about a watt of power. Yeah, and you can just plug something into here and then do an analog readout. Yeah, so power in 1.2 watts. Yeah, so that's actually really nice in terms of power consumption. So you can, for example, run it off of a battery, yeah, which with other gauges is not that easy, not that recommended. But with a Pirani gauge, you can essentially run it off of a battery for quite a while, because it's a very simple, small package. So you can see it's about the size of, it fits pretty neatly into the palm of my hand. And this is why it would be very nice to have Pirani gauges that go to a little bit lower pressures. Okay, and with that we'll actually move on to the ionization gauges. So ionization gauges, let me just make a new slide. With ionization gauges, essentially we have hot filament gauges. So we have a hot filament, and we have gauge, and we have a cold cathode gauge. And so the way that they work is that the hot filament gauge, we have, I'll draw them separately. But let's maybe just show what the upsides are. So hot filament gauge is we have some kind of hot filament where we get ionization, and then we measure the ion current. Yeah? So we get some ions and we measure the current. With the cold cathode gauge, we essentially get field ionization. I'll just draw that as a bit of an atom probe field ion microscopy thing. But it's a little bit more complicated than that, because we have the whole thing with the magnets and everything again, but I'll draw that later. And so that the upside of the hot filament gauge is it has no magnetic fields. Which, in atom probe we don't really care. We can live with magnetic fields. It's very simple. But it produces heat. Oh, and I should also say it can be used to go to very low pressures. So essentially 10 to the minus 12 millibars you can measure with a gauge. So if you go to physicists that, for example, do antimatter experiments, atomic clocks and the like, that really have extremely good vacuums, they have no way apart from them experiment itself to measure the pressure. So they don't have any of those gauges anymore at all. So this is just a gauge, means I plonk that thing onto my system and it gives me a pressure reading. In many other cases, I have nothing but the experiment to tell me what the pressure is. And there are special versions of the hot filament gauge that can get us down to 10 to the minus 12 millibars, which is very good. The problem is it produces heat. So if you want to cool your sample to 2 Kelvin, it's not good. If you have something, that radiates a lot of infrared heat into your system. And the other thing is that it has a finite life. But the finite life is essentially called by collisions with the gas atoms. So if you're at a very, very good pressure, you don't have to worry too much about the finite life. Whereas the cold cathode gauge, the good thing about it is it gives no heat. Yeah, so it doesn't produce any heat, but it has magnets. And the reading depends on the gas type more than on the hot filament gauge. It does as well, but on the cold cathode gauge, it's more pronounced. Reading. Depends on gas type. And in atom probe tomography, we find both. Some people use hot filament gauges, some people use cold cathode gauges. In my systems, I use cold cathode gauges. The Leap uses cold cathode gauges. And the main reason why in my systems I use cold cathode gauges is because hot cathode gauges can dissociate water vapor. So if you've got residual water in your system, and as I told you with polymers and the like, there's always going to be a little bit of residual water. The hot filament gauges can dissociate the water to hydrogen and oxygen. And that obviously, if we want to measure hydrogen, can be a problem. So you're a little bit better off with cold cathode gauges. But in all honesty, if you want to have extremely good pressure, switch off the pressure gauge. I know it means you're going to be flying blind with pressure, but if you're convinced enough that your atom probe is going to hold the pressure during the experiment because you've seen it 1,000 times and it's always worked, it's a good idea to switch off the pressure gauge to avoid things like that happening. Even though I said that the pressure gauge is actually pumping itself, but in some cases, in terms of hydrogen, it's not always really optimal what it does. Okay, so then let's go to the hot cathode gauges. And the hot cathode gauges that we are using these days are almost exclusively so-called Bayard-Albert types. So we have hot cathode gauges, and the ones I'm talking about are the Bayard-Albert type. Historically, you'll find a whole bunch of different designs, but this is the one that that most people seem to have settled on. And the way it works is essentially you have a coil, a heated coil, and I should probably draw it in a hot color. It's a heated coil, and then you have what the hot filament gives off is actually electrons. So in this case, the hot cathode doesn't directly ionize the atoms, but it only provides electrons. There are other hot cathode gauges where that's a little bit different. And then we have a cage here. We have a cage here. And within the cage, we've got a collector wire. And usually the hot cathode is at about plus 30 volts and at, you know, some glowy, reddish glowy temperature. Then we have about plus, let's just say plus 200 volts roughly, and the collector is at 0 volts. So what will happen is you will get electrons coming out of here, yeah, and those electrons are going to be sucked into the that mesh. And what they are going to do is, if there is some neutral atom, and I don't know what is a neutral color, gray is a neutral color, yeah, so this is our neutral atoms. They're floating around somewhere in space, or neutral molecules, doesn't need to be, yeah. They're floating around somewhere, and if they get hit, then our neutral goes and becomes positively charged. Yeah. Goes and becomes positively charged just through impact ionization, Stoßionization. Sorry, I only know the word in German. And then this way produce a current, because the electron goes to, here. Yeah. From the ionization, no, I had this color for the electron. The electron goes into the collector, into the anode grid, and the positively charged ion goes towards the collector. And so we've produced a current through that, and that is our measurement signal. This is actually you can actually have a very large area where you can produce that cross section, which means you can get a pretty good collection efficiency. And if we then plot, pressure P, actual pressure P versus IC, so this is our anode cylinder, this is our ion collector, and at the ion collector we have the collector current IC, and this is our hot cathode. Essentially what we get here is, if we're at very, very low pressures, we have something called the X-ray limit. And I'll get into that in a second. And so essentially, in a relatively wide range of pressures, and then we get breakdowns at about 10 to the minus 2. So this would be about 10 to the minus 2 millibar. Sorry, I should have, let me just redo that here. So this would be roughly 10 to the minus 2. So this would be pressure in millibar. And this would be ion collector current. Essentially, if I extrapolate up down to here, this is what we call the X-ray limit. And our measurement area, where it's pretty linear, goes down to here would be about 10 to the minus 10 millibar, and here we would be roughly 10 to the minus 11 millibar-ish for the X-ray limit. You can extend that limit a little bit by having an extractor type gauge. I'm not going to go into detail what an extractor type gauge is, but you can additionally extract ions, and then go down to about 10 to the minus 12 millibar. X-ray limit just simply means that the amount of current that you produce just by X-rays hitting your gauge and knocking electrons out of your ion collector is going to be larger than any signal you measure. So you're essentially at a loss in terms of measurement. But you can go down to 10 to the minus 11 pretty solidly. So most hot cathode gauges allow you to go down to those pressures, 10 to the minus 10 pretty well. And this makes it pretty well suited for measurement for atom probe or any other ultra high vacuum system where you don't have anything that produces too many contaminants. So if you periodically put gases in that would crack at so hydrocarbons and stuff like that would crack at the hot cathode, it's probably not a good idea to use one of those gauges, but we don't usually do that. But there have been machines, atom probes that were used for catalytic experiments, and in this case, if you put CO in and the like, I'm not quite sure if a hot cathode gauge will last super long. But there's probably people more qualified than me to make a comment about that. Okay, and as the last gauge that's important for us, we have the cold cathode gauge, and the cold cathode gauge is actually very important for us because it is probably the most popular gauge for ultra high vacuum measurement for film and atom probe. Cold cathode gauge, and I've mentioned it before when we went to the ion getter pumps. It's essentially an ion getter pump, and any ion getter pump can be used as a cold cathode gauge, by the way. So if you have an ion getter pump and you switch it on, it will always give you a pressure reading, and the reason is it can be used as a gauge, just like any cold cathode gauge can be used as a pump, not particularly efficiently, but it will pump. And we have the same setup again. So we have a cylindrical anode. We have a cylindrical anode, and we have plate cathodes. So they are both at the same potential. Then we have a measurement of the current here. So we measure the current here. We measure the current I here. And we have a high voltage power supply here. And just like with the ion getter pump, what we get is we get any where was my neutral color again? Any neutrals coming in, and the neutrals are going to be hit by electrons that have been ionized by previous electrons. And so if I have an electron, the electron is going to be accelerated from the cathode to the anode. So it wants to go here or here. It's probably closer to, anyway, I've drawn the line already, so it's going downwards even though it's short upwards. Sorry, it's unphysical. And just like before, we have a magnetic field B that goes in this direction. So So our electron does the spiral motion again, right? So our electron does the spiral motion again until it hits the cathode and hopefully ionizes a neutral, hopefully hits a neutral and ionizes it into an electron and into a positively charged ion, and a positively charged ion would then obviously hit the cathode. And we're again measuring that total current. So we're measuring that total current. Obviously, you can see that further that this is sort of kind of an equilibrium between the process to generate electrons from collisions, while also so generating electrons from collisions, and those electrons need to collide with other atoms. So as a result, you need to have a certain amount of gas in there for it to ignite. And this is why the lower the pressure is, the longer it will take for a cold cathode gauge to ignite. If you switch it on at 10 to the minus 5 millibar, it will be here immediately. If you switch it on at 10 to the minus 10 millibar, it might take 15 minutes until it's collected enough dirt, enough gas for it to be effective. The thing is, of course, in this case that the ionization cross-section and the ionization potential makes quite a difference. So the harder something is to ionize, the more the pressure reading will change with the gas, so that you will get a gas dependency. And that gas dependency is that the pressure is equals a factor K times P, the pressure on the gauge, and the K typically gauges are, so this is for a Pfeiffer. So the example is a Pfeiffer IKR 270, which is the gauge on the LEAP, or the gauge that I use on the FIM and on the Oxcart and so on and so forth. So it's a very popular one because it's essentially a cold cathode gauge that goes down the lowest. Yeah? And if you look at gas versus this K factor, and for air, we have factor 1, and it's just because it's calibrated for air. Yeah? If you have xenon, so something that is fairly easy to ionize, then we have a factor of 0.4. If you have argon, which might come from leaks and the like, we have a factor of 0.8. If we got hydrogen, the factor is 2.4. So our measurement, if we have 2.4 times 10 to the minus 10 millibar hydrogen in there, it will show 1 times 10 to the minus 10. Okay, so we are missing hydrogen, and if you have something with a relatively high ionization potential like helium, it will even be 5.9. So this might be important if you're doing FIM, and you're trying to measure the gas pressure. You need to be aware that there's a factor of almost 6 between the measurement between the gauge reading and the actual pressure. And of course, if you've got some kind of mixture of the gases, it becomes extremely hard to figure out what the actual pressure is, because you would need to know what the individual concentrations of the gases are that you have in there in order to interpret what the gauge reading is. And this is really the difficulty with these gauges, that this is not super easy to figure out. With all of those gauges, you will usually get a pressure versus pressure effective graph. So this is, or we should call it pressure gauge, and it's gauge versus pressure actual. And you will see that this factor actually applies at relatively low pressures. At high pressures, you will have deviations from that. For example, and we're talking about 10 to the minus 4 and up. So we prove usually about 10 to the minus 4 and up. You will see, for example, that for should be the other way around. That for hydrogen it will go up a little bit. For xenon and krypton will go up a lot. Whereas for things like helium, it will be pretty stable. Yeah. That just means if you go to your friends and you show off, you want to show off and you say, hey, my atom probe has a pressure of XYZ, then I will tell you that that does not, so your pressure is XYZ and it's lower by a little bit than the pressure in the other atom probe, then I will have to tell you that does not mean much. Also, at low pressures, at P less than about 10 to the minus 9, the delta P, so the error, is around 50%. Now, so we also have a relatively large measurement error of about 50%. The gauges are usually pretty reproducible, but they do have quite a significant amount of scattering. So do not give too much attention to the actual pressure reading. Do some critical thinking about what the pressure reading could mean in terms of, okay, have I calibrated it against something that I know? Do I understand what kind of gases I have in my system, so that I can properly interpret what the pressure is in the system. So far, I only know, I think Chalmers has done that, but you always have the option to put a residual gas analyzer on your system, which is something that can really help you figure out if you've got something outgassing. The problem with residual gas analyzers is just they tend to be a source of residual gases. Might sound like a bit of a joke, but especially they can spit out some hydrogen. That's why, unless you really have a specific question to ask where you need some residual gas analysis, it's usually not that great an idea to put a residual gas analyzer in. Also, they're big, they have a finite lifetime, and they cost a lot of money. That's why not a lot of people have them. But if you have some specific questions about the vacuum, about what kind of vacuum. What kind of gases you have in there? Do you have air leaks? Do you have things coming out of your specimen? I think at some point it was interesting to see if you field evaporate, if you, for example, field evaporate an oxide or a nitrate or something like that, do you produce neutrals? Can you pick them up with a residual gas analyzer? They can be pretty sensitive to small amounts of gases. So yeah, there were some interesting questions to be asked there, but I haven't heard much of that in recent days, really. So the last thing I want to do in this part of the lecture is then a little bit of show and tell again. So let me switch over to the demo. And I've also mentioned that there are combination gauges. And this here is a typical combination gauge. This particular one is from Edwards, and it's a digital one. So you can plug it in, and it has a serial communication interface here, so you don't need anything but a 24 volt or something between 15 and 40 volt DCs. Takes about 2 watts, and then you can measure from ambient pressure down to about 10 to the minus 9 millibars, because it's got an Pirani gauge in there and a cold cathode gauge. So you can look inside and you can see a little bit of the innards of the whole thing. And this is a very common gauge to use in process equipment. Yeah. And the different gauges you can get, the important differences for us is this is a gauge, that is not bakeable. So I have no means to take off the electronics, which means it can't get any hotter than I think 60 or 80 centigrades at the flange, which is not great for baking. So for a load lock, this is fine, but this is not a good gauge for a buffer chamber or main chamber. For a buffer chamber or main chamber, you would have gauges where you can remove the electronics, so that during the baking you can heat up, you can get the gauge usually to, without the electronics, about 250 degrees C, which is great. The reason why this is, if you compare it to the Pirani gauge, you can already see that there's a massive difference also in weight. Yeah? So this thing weighs a lot more because it has the magnets for the cold cathode gauge part, and you cannot bake it. Unfortunately, I don't have any gauge here right now that I have taken out of a system where I can show you the removal, but essentially usually you have 2 or 3 screws that you can take off, and then you can take the electronics off, and then obviously the gauge doesn't work without the electronics, but you can then bake to high temperatures. Obviously that means while you're doing that, you do not have the ability to measure. That's why there are also very special gauges for ultra-high vacuum systems that allow you to measure while baking. And these look a little bit different because you can see here you've got your cold cathode part, and here your electronics. And they have a long stalk in between, about 20-25 centimeters, and electronics sit here, and the actual readout sits here. So you can have the front part at a relatively high temperature, baking temperature 150 degrees, no problem, and then have the actual electronics outside of the baking tent or whatever, aluminium foil or whatever you use to facilitate the baking. And this allows you to measure the pressure during pump down. Otherwise, during baking, otherwise it's pretty hard to track whether your baking was successful or not successful. And with that, with those gauges, you can see that. They then usually just cold cathode gauges and nothing else. But yeah, those gauges work very well. In terms of power consumption, you could run it out of a battery. It takes about 2 watts. So these combination gauges take about 2 watts, which is fine to run it off of a battery. But they just weigh, I don't know, maybe 2 kilos, 1.5, 2 kilos. And this thing just weighs, I don't know, 50 grams, 100 grams, a lot less, because it doesn't have the magnet on it. Good, and with that, I think we've made it through the most important parts of vacuum measurement. Obviously, if you go into the details of vacuum measurement, there's a whole lot more to learn. But I think if you're just interested in what does the pressure reading I get on my atom probe mean, and how can I interpret that, I think what we went through today should give you a pretty quick rundown and some idea of the meaning of pressure readings in atom probe tomography. Great, and with that I'll conclude the part on pressure measurements.